Okay, so last time we introduced free cumulants, and the idea is that freeness is easier to describe in terms of cumulants than in terms of moments. And we introduced those cumulants, and we have to understand them better to see really their usefulness for the description of freeness. And for this, it's a crucial property of them is how they behave with respect to the multiplication of arguments. That's the main thing which we want to understand at the moment. So let me recall what we want to do. So we have arguments, a's, little a's, and we multiply some of them together. And then we want to compare the cumulants of those two situations. So we can have something like a1, which is the product of some of the little a's. I1 many of them. Then A2 is the product of the next one, so I1 plus 1 up to I2 up to AM. That's the product of the last ones of the little a's. It's AI M1 plus 1 up to AIM. And AIM we also call N. Okay, so we have those little a's in our algebra. Let's say we know the cumulant of those, and the question is how can we calculate the cumulants of the capital A's? Okay, and of course it's clear. We want the cumulants. The cumulants are given by the moment in terms of Möbius inversion. On the level of the moment, the relation between those two guys is very easy, because this was essentially associativity. So in our functionals, moment functionals, we can just remove the comma, so we can move it as we like. And so in this context, it's very easy. And so actually, this gives us a mapping from the non-crossing partition of m elements to the non-crossing partition of n elements, such that the moment functionals are related. Also, what we had in this context was a mapping which we called head. So this goes from non-crossing partitions of m elements, so partition of the A, capital A's, to non-crossing partitions of n elements. And the crucial property is that if I take the moment functional of, let's say, tau of the A's, A1 up to AM, and this is the same as the moment functionals of the tau hat applied to the little a's, A1 up to AM. This mapping was just, an example, A1, A2, A3. Let's go to A1, A2, A3, A4, A5, A6. In the case where A1 was, let's say, A1, A2 was the product of three of them, A2, A3, A4, and A3 was the product of the remaining twos, A5 and A6. And then if we have a non-crossing partition here, we just inflate the blocks here to be a block here of the little a's which correspond to the capital A's. So this one here remains a singleton, it's only A1, but A2 is the product of A2, A3 and A4. So this goes to this, and the capital A3 goes to this one. Okay, so tau hat of this is this mapping, and of course it is clear that if I take phi tau of this guy, so this is the product of phi of A1 times phi of A2 times phi of A3, that this is the same as the phi of this tau hat of this guy. Because this, for this mapping also tells me I have to take phi of this, I have to take phi of the product of those, which is of course phi of A2, and I have to take phi of the product of those, which is of course phi of A3. Okay, so in general we have this relation. So on the level of the moments, things are very easy, but now of course we have to transfer this to the cumulants. Essentially we have, if I want to have the cumulants of those guys, with Möbius inversion, I express it in terms of the moments of this, then I go over to this, and then I do Möbius inversion again, going back to the cumulants of the little a's. But of course, the summation is now running only over some subsets, and we really have to understand what this is. And it turns out that the crucial information we need for for doing this is the fact that actually non-crossing partitions are not just a coset, but they actually form a lattice. This means I have a minimum and a maximum for each pair of partitions. So let's formulate this in the next proposition. So lattice is a special coset which has a minimum and a maximum, or even a joint. The statement is the following. For each n and n, we have our non-crossing partition lattice, and I'm claiming that this is a lattice. Coset up to now, nc of n was just a coset, so we have a partial order, but I said this partial order is actually a lattice. And what does this mean to be a lattice? It means that we have two operations which are like a maximum and a minimum. Of course, I mean maximum minimum, you know, it is in a total order, but we can also define it for partial order. So this means whenever I have two elements, and sigma in my nc of n, then I'm claiming that there exists a maximum of them, so there exists. And what is a maximum? I mean, a maximum should be something which is greater than each of them, but it should be the smallest of those guys. So there exists, and that such a thing exists and is uniquely determined by this, that's a property which is not satisfying all cosets. But this is what gives it the lattice structure. So there exists a unique smallest tau in my non-crossing partitions, which has the property that it is bigger than each of them, such that, so this the smallest tau, the properties that tau is greater or equal than pi, and tau is greater or equal than sigma. Okay, so we have to prove that such a guy exists. Okay, if this exists, then this is usually denoted by this symbol, which looks like union line, and this is called, in this coset context, usually the join of pi and sigma. It's called join. Okay, but I mean, you could also say it's the maximum. Max of pi and sigma. Good. Okay, and of course there's a dual object, namely a minimum. So we also have a minimum, which is then called a meet of two guys. Okay, this is the first part. The second part, that also for each pair pi and sigma, is called sigma, the non-crossing partitions. There exists a minimum, and what should be minimum? A minimum should be smaller than each of them, but a minimum should be the largest of those which have. So there exists, again, unique, largest. Non-crossing partitions with the properties that it is smaller than both of them. So such that tau is less or equal to pi, and tau is less or equal than sigma. Okay, if such a thing exists, then we call it the meet of pi and sigma, or the maximum. And we denote it in the following way. So this tau is denoted by pi meet sigma. Okay, this is called meet, or I always forget which is the meet and which is the join, so we usually have to probably talk about the maximum mean. This is somewhat easier to remember, at least for me. So pi and sigma. And of course the meet is something like the intersection, and the join is like the union. Context of sets. Good. Okay, so we have to prove that this is actually true for non-crossing partitions. So what we have to do, I mean, whenever you give me a pair of pi and sigma, I have to tell you how to get the mean and how to get the joint. Okay, one of them is actually quite easy and straightforward. Also, the definition looks symmetric, but I mean, one you can really write down directly, and the other is a little bit more complicated. Also, it's not, okay, the construction of them is not as easily dual as the definition. Okay, so let us consider the mean. This is the easier one. So this is the minimum of them. And so, I mean, if I take the minimum, if I have pi and sigma, I need something which is smaller as both of them. So this means the blocks of this mean must be contained in the blocks of pi and in the blocks of sigma. And so, of course, the first guess is, what should I take? I should take the intersection of the blocks. All possible intersections of the blocks, and that's actually what does the job. So for, let's say, pi as the blocks B1 up to BR, and sigma as the blocks W1 up to WS. So pi has R blocks and sigma has S blocks. Then we just take the intersection of them. And I'm claiming that this is really the mean. And this is actually easy to check. That's somehow clear. So we have that. This intersection. That's really. I mean, that's the thing you really need, and this is the biggest one of all possibilities. So we have that the mean of pi and sigma is given by the partition where the blocks are the intersections of a block of pi and a block of sigma. So I take all possible intersections. So this means I is between 1 and R, and J between 1 and S. So I take a block of pi and I take a block of sigma. And of course I only take the blocks which are not empty. Of course there are intersections which are empty, but of course they don't count for this one. So I just take the ones for which this intersection is not empty. And of course this gives me a partition of my set 1 up to n, and of course it's also non-crossing, because I mean because both of them are non-crossing, and this really has these properties. So that's quite easy to see. I'm not going with those little things formally. You should think about them, but maybe just an example. So just to make clear what we have here. So let's say, for example, I take as pi, I take partitions, non-crossing partitions of 4 elements. And let's say I take this, and I want the mean with this one. So here I have a block of 1 element and a block of 3 elements, and here I have 2 blocks of 2 elements. And so what is the mean of this? I take the intersection, and of course it's clear what I'm doing here. Essentially, I mean, I'm checking for elements. Are they connected to some other elements? If they have to be connected in the mean, I mean they must be connected for each of the 2 partitions. For example, this guy, I mean here it is connected to this guy, but here is connected to nothing, so here we'll have a single. Okay. And this guy here is connected to other guys here. You see this guy is connected, let me see. So this one is not connected to anything. I mean here it is connected to this guy and to this guy, but here it is not connected to those two. So this means this is not connected to anything. Okay. But of course this and this, they are connected both here and here. So I have here this block. So these are exactly the blocks which are given by taking the intersection of those blocks. Or another way of saying it is that if two elements here are connected, if they are connected here and connected here. So we could also say that P is in the same block in this partition pi meet sigma as Q if, only if, P is in the same block as Q for the partition pi, and P is in the same block as Q for the partition sigma. Okay. So this means this meet is just the end or the intersection, as you And of course, then you would think that for the join, it's just the union and it's just the OR. No? It's either connected here or it's connected there. But actually, this is not true, no? Which makes it a little bit more complicated for the join. So the join. But I'm still claiming there is a join, but it's not given in the same direct way as for the meet. So maybe you should note, and maybe later we look at this more carefully, that the first guess, which is one just replacing the end by OR, first guess would be that they are in the same block with respect to the join if they are either, or if they are in the same block with respect to Q, with respect to pi, or if they are in the same block with respect to sigma. But this does not work. Maybe it's clear to you, otherwise we will later see the example. We will talk a little bit about it later, but maybe first I should show that still we have a join, and actually we can reduce the join to the situation of the meet. Because the join is defined to be the largest element which has some properties. But the largest element, this is actually the meet which you already have. Which means we can reduce it to this situation. And the fact, we take the largest element with some properties, so we should have elements which have these properties, because otherwise the meet is not clear. No? Okay, so the meet of the empty set is not clear what this should be. We need something, but at least we have one join, and this is the maximal element. So we have one element which is bigger than anything. We have what we denoted by 1. That's what we already saw before. That's the partition consisting of one block. This is larger than anything, so this means we have a join for anything. So we find, whenever I have a pair, I always find at least one element which is bigger than each of them. The one element, this has this property. And then we just take the meet of all elements which have this property. And the meet is already defined. So this means we can reduce the situation of the join to the meet. But we can reduce join to the meet. Okay, so first of course we should observe that if I have the meet of two elements, of course I have the meet of a finite number of elements, just by induction. Okay, so by induction we have meet for any number, and of course we only have finitely many elements, so it's a finite number of any finite number of crossing partitions. So this means, we do not only have pi, the meet of pi and sigma, but so whenever I have, let's say, k many pi's, I have also the meet of them. I have pi 1, meet 2, meet and so on, meet pi k. For any k greater or equal than 1, then pi 1 up to pi k. And of course, for k equal to 1, of course, we only have pi 1, the meet of pi 1 is pi 1. And of course, we can also, as before, the blocks of this guy are just given by taking the intersection of all the blocks of all those guys, just by induction. Okay, so this is something which we have. And then, for the join, we have at least one kind of join, namely the maximum element. And then we also have maximum element, 1n, which is the join over everything. So if I want to take the join of all my partitions, of course the maximum element is the join. So at least for one situation it is clear that we have a join, which is the join over all. Good. Okay, and now we can write the join of something as the minimal element with some properties, but the minimal element is the mean. So then sigma, which we have to define, I mean this should be the smallest element, so it should be the mean of all taus which have the properties which the joint should satisfy. So it should be the mean of all taus n such that tau is greater or equal than pi and tau is greater or equal than sigma. I mean this is just a definition of the joint. Okay. The crucial thing is, I mean, whenever I have here a finite set, I know that I have a mean. The only problem is that this finite set here should not be the empty set. So there must be at least one tau which has this property, but we know that there is at least, there's always one which has this property, namely the one. So this guy here, this set here is not the empty set, since it contains always maximum element. Okay, and then there exists the mean of this, and this is the joint of this. So this is in a sense not a constructive way as before, but at least, of course, we have to look for all those taus, and then we have to do this, but it's more complicated. But it gives us the joint. Good. Okay, so. And now maybe let me make a few remarks, maybe to a more concrete way of also describing the joint. Now, of course, if you look more carefully on this, we still can describe the joint somehow, but it's not just given by taking the union of blocks. And maybe the first remark is that actually we could do the same things, not in a coset of non-crossing partitions, but in a coset of all partitions. I mean, for all partitions, of course, we can also define the order, smaller or equal, and this is a coset, and again, it turns out that this is also a lattice. And for the mean, actually, the mean is the same, whether you consider it in all partitions or in the non-crossing partitions. But for the joint, this is not the case. This also shows you that the situation is not so symmetric. Okay, so first note that this coset structure we also have for all partitions. So note that if I have just partitions, not necessarily non-crossing ones, you can also define the order. So saying that pi is less or equal than sigma in the same way as for non-crossing partitions. So this just means that any block of pi must be fully contained in some block of sigma. Good. Okay, so this is also a coset, and in the same way as here you can ask the question whether it's a lattice, and actually it is also a lattice. So Pn is also a lattice, and the mean is given in the same way as we have it here. Okay, so we just take the intersection. So the mean of Pn restricts to the mean from NCN. So this means if I have two non-crossing partitions, which of course I can consider as elements in all partitions, then I have essentially two operations. I can take the mean in all partitions, I can take the mean in the non-crossing partitions, but it turns out this doesn't make a difference. For the joint on the other end, it makes a difference. Because there the non-crossing condition becomes important. For the mean, I mean the non-crossing is automatically satisfied by doing this operation. But for the other one, for the mean, we have to observe that we want, whether we want a partition which has this property or whether we want a non-crossing partition which has this property. So, continue here. But for the join, both operations are in general different. Both operations are different. Okay, of course, we should see this with an example. So let us take the join of partitions in 4 elements. I mean, they are non-crossing partitions, but they are also partitions. So I can take the join in the partitions. And what should this be? This should be the smallest partition, which is smaller than each of them. Okay, so what is this? Okay, so it's clear. I mean, it should be bigger than this one. I mean, this and this guy should be connected. Okay, so this means I would like to have a block like this. On the other hand, if it is bigger than this one, then I mean this and this should be connected. So this means I also want to have a block like this. And in all partitions, that's okay. That's the smallest one which does the job. Okay, but this is now a crossing one, which means in the non-crossing partitions we don't have this element. So if we want to have a smallest one which is bigger than this one in the non-crossing partitions, we must get rid of this crossing, which means we must merge those two blocks together. So this means non-crossing partitions meet the same two elements. This is actually this guy. Okay. So you see, I mean, the meet is more, the join is more complicated because we could first take the join in both, in P of n, and then to get rid of the non-crossing partitions by merging blocks which have a crossing. Well, and that's true in general. So essentially, we can compare the joins in both lattices. So in general, the join in C is given by taking the join in all partitions and then merging blocks together which have a crossing. Like here, I mean, if you have two blocks, they have a crossing, so I must make one block out of those two. Join P, and then merge one crossing blocks together. Okay, so you see that this is one reason why maybe this idea that for the join we could take this operation doesn't work because we would get crossings which we should get rid of. Okay, but even if we ignore this, then it's still not true that we should just take the OR operation. No? So even in P, it is not true that we get the join by just taking the union of blocks. No? So maybe we should think a little bit of this. Yes. Okay, so the last part of this remark is that even in Pn, even in all partitions of the elements, join P join sigma, maximum is not just given by saying that they are in the same block with respect to the join, if they are in the same block with respect to pi, or in the same block with respect to sigma. It's not given, but what one has to do, has to allow a longer alternating connections of elements via pi and sigma. Alternating connections via pi and sigma. So here we are just saying, okay, they might be connected because they are connected in pi, or or they are connected because they are connected in sigma. But that's not true because there might be intermediate guys which are also connected. And there might be something in between which is connected to pi, and this is connected by a sigma to something, and this again by a pi, and then in the end maybe you are connecting the two guys which you are interested in. I'll make an example. If we want to take, let's take the join of something like this, and okay, so these are non-crossing partitions of 8 elements. Here I just have pairing, here I have 3 pairs and 2 singletons. And now the question is, so what is this? And now, for example, the question is, for example, this guy and this guy, should they be connected in the guy? Of course, they are not connected here, and they are also not connected here. So if you would just take this definition, they are connected in the join. If they are connected in one or the other, then this is not true. But actually, I mean, you see, of course, this guy here is connected to the second guy here. But then this guy is connected to the next guy here, and this again here, and so on. So we have alternating sequence of connections, which in the end connect this guy with this guy. And so we see that actually for the join here, we have to connect everything. So actually the join of this is just one partition. So this is just but I mean here, in each of them, not so many guys are connected. But alternatingly, so if you want to know whether this and this guy are connected, I can run through a chain. If this guy is connected to something in one of them, this is connected to something in the other, and so on, and at the end I'm getting this connection. And that's the right way of describing the join in the non-crossing, or in all partitions. And then, if we have non-crossing partitions, we might also have to merge blocks like this. Good. Okay. So this shows the meat, or the join is a little bit more complicated. Good. But now, having this lattice structure, we are now able to write down the connection between the cumulants of the capital A's and the little a's. So let me now give you the theorem, then prove it. But there's now a very nice and clear description how the cumulants of the capital A's and the little a's are connected. And for this, I mean, we use this join formation. But this is one of the main theorems from the I mean, it's maybe a technical theorem, but it's very important because it's useful in many instances. We can use it for proving many things. So here's the theorem. I mean, the main theorem we are after is one how to characterize freeness in terms of cumulants. But this is a crucial ingredient in the proof of this. Okay, so we consider the situation of a non-commutative probability space in phi, and of course we have corresponding cumulants, and the connection of kappa pi and non-crossing partitions of arbitrary number of elements, they are defined in terms of the phi. The phi gives me the moment functionals, and from this I calculate the cumulant functionals via Möbius inversion or lattice of non-crossing partitions. So those guys should be corresponding cumulants. Okay, now I'm looking on the situation which we had before. I have, let's say, n many little a's, and I multiply some of them together to the capital A's. So this was this situation. I'm not writing down again all the data, but this was as we had before, as in 16. Just again, the crucial thing is that I have capital A's, which are the product of some of the little a's. I multiply and then I have AM, where I'm going from IN minus 1 plus 1 up to IM. And this IM is multiplying N. So I'm just multiplying the last of the A's together. I have A1 up to AN, and I multiply all those pieces of them together. And of course, we also had this mapping head, which corresponds, which gives me the information how many I multiply. This depended on the situation of the eyes. Good, but now what I really want is how to relate the cumulant of the capital A's to the cumulant of the little a's. There's a very precise formula. Let me take an arbitrary cumulant indexed by a non-crossing partition. If I want to have it of the capital A's, it should be a non-crossing partition of m many elements. So then we have for tau non-crossing partition of m elements, the kappa tau of m1 up to am is actually given by the sum over cumulants of the little a's, but I'm just summing over cumulants for specific pi's, which have something to do with this tau, and of course are related with this mapping here. So I'm summing over pi non-crossing elements n, not all of them, we say in a minute, and I'm just taking here the kappa pi of a1 up to an. Okay, I'm not summing over all pi's, but I'm summing only over the pi's such that the maximum join of p and 0 m hat is equal to tau hat. So this hat mapping maps non-crossing partitions of m elements to non-crossing partitions of n elements. So this guy and this guy are non-crossing partitions of n elements. So here I'm in the lattice of non-crossing partitions of n elements. Okay, I mean this is, so here I'm taking the smallest element, the head of this, and here I'm taking the head of this mapping here. Okay, so this is a very precise formula, and maybe in particular, usually those guys here are multiplicative with respect to the block, so usually you only need the kappa n's, the kappas corresponding to the maximum partition. So maybe let me also write down the formula for this case. In particular, special case of this, if I take tau equal to the maximal partition of m elements, then this here is more or less the same formula, but here I just take kappa m of m1 up to am. This is given by summing over non-crossing partitions of m elements. So here I have kappa pi of a1 up to an, 4, this is also n. And the condition is now that the join of pi with 0 m hat should be now tau hat, but tau is now the 1, so this should be the head of 1m, but this is 1n. So the maximal element under this mapping head goes to the maximal element. For the minimal element, this is not true. I mean, this guy here is not the minimal element in NCN. But the 1m hat is the same as 1n. Okay. Good. So this is. So we have to prove this, but maybe before we prove it, maybe let me do an example just to show you, I mean, what really this formula means, and that we can also use it for getting interesting information. And maybe let us look for the situation where I'm multiplying things actually, where I'm taking the product of a semicircular element with itself. So we already have seen that the square of a semicircle is a free Poisson. Okay, for both we know the cumulant, so maybe we should check that we get this from this formula. And before we have seen it by not directly, but we can also now see whether this formula gives us this information and what it really means to apply this formula. So before we prove it, I mean the proof will be quite formal. we just do twice Möbius inversion, and we have to see that we get what we have to get. Also, and if you have this formula, it's not so hard to prove. You just have to write down things in the right way. It's more having the idea that there's a formula like this, and then maybe also what this really means. Good. Okay, so let me look on this example, and then after the example we will do the proof. Okay, so let us take the standard semicircular element. So we denote this by S. Standard semicircular element. And as we have seen last time, semicircular element is determined by the fact that only its the second order cumulants are different from zero. So actually we have the cumulants of this S, so I take the kappa n, and all the arguments are equal to S, that this is actually 1 or 0. And it is 1 exactly if n is equal to 2. This is 1 or 0. It is 1 if n is equal to 2, otherwise it is 0. So this is just another way of saying that the moments of a semicircular element are given by counting the non-crossing pairings. Because if I extend this to a multiplicative function, then kappa pi is equal to 1 if pi is a non-crossing pairing and 0 otherwise. Good, but now, so we know the cumulants of S, and now I want to look on the cumulants of S squared. We have seen S squared is a free Poisson, and we also have seen a free Poisson of parameter 1 has cumulants all equal to 1. So we should see that this formula tells us that the cumulants of S squared are all equal to 1. So let us check. S squared, x, is a free Poisson. Free Poisson is parameter lambda equal to 1. And this means, we also have seen this, that the cumulants of x are just 1 for all n. So that's what we want to see. And so we use this formula from the theorem. So what does this tell us? So if I want the nth cumulant of x, this is of course x is now s squared, so what I have here, in each argument I have now s times s. S, 1, s, and my formula here tells me I can reduce this, express it, in terms of cumulants of the s themselves by summing over specific parts. So I have to sum over non-crossing partitions, and of course how many elements do I have here? I have m arguments here, but each of them is the product of 2, so I have 2 elements, and the condition is that the maximum of pi and 0 n hat has to be 1 in these 2 elements. So this one. So I'm using this formula here, specification where I do about kappa m, and I'm summing here over the kappa pi of s, s, and so on. Now the s's are just single arguments here. So here I have 2 m slots, 2 m arguments. Here I only have m arguments, and each argument is the product of 2 s's. But here I have 2 m. Good. Okay, and so first of all, as we said before, of course this kappa pi here is the extension of this, and it is 1 if pi is a non-crossing pairing. Because this is product of the kappas corresponding to the blocks, and the kappa of the block is 1 if the block has 2 elements, otherwise it is 0. So this means this is 1 if all blocks have 2 elements, which means it is a pairing. This here is either 1 or 0. Depending on whether pi is a non-crossing pairing of 2 m elements or otherwise. So this means again what I'm doing here is I'm just counting pi's. I mean, I'm summing over pi's, we will give this some property, and the contribution of them is 1 if pi is a non-crossing pairing. So this means what I'm doing here, the sum is only running over non-crossing pairings, because the other terms don't give a contribution, and then just each of them counts 1, so I'm just counting the non-crossing pairings which have this property. So what I have here is the number of non-crossing pairings of 2m elements, but of course I'm only summing over those which have this property. So I'm counting the non-crossing pairings such that pi and join this 0 and hat is usually 1. Good, so we have to understand what this condition here means in this specific context. Okay, first of all, what is this 0 and hat? This is the partition. The blocks are given by taking the positions where I multiplied the arguments together. And here, of course, I'm just multiplying always 2 arguments together. So this means this 0 and hat has m blocks, and they are telling me that I multiply the first and the second element together, the third and the fourth element together, and so on. So the blocks are consisting just of 1 and 2, 3 and 4, 5 and 6, and so on. So it's just taking those 2 pairs of neighboring elements together. Yeah, okay, so let us note this first. So the 0 m hat, and for this specific hat, this hat mapping of course depends on the situation which we have, how we multiply. But here we are multiplying the first and the second element together, we are multiplying the third and the fourth element together, and so on, up to the last 2 m elements. The last 2 elements, which are the 2m minus first and the 2mth. Okay, so this is the 0 m hat. And now I have to look for non-crossing pairings such that the maximum of pi and this guy is everything. This is the 1. So what I have now is I have my 2m elements, and I have the 0 m hat, which is this guy. Connects the first and the second, the third and the fourth, and so on. It's always connecting something like this. And now I have to look for pi's such that the maximum between pi and this guy is everything. So this means those 2 guys together should connect all points. We sigma m hat already connects this with this, but the pi now must do the remaining connections. And so what are the possibilities for this? And pi, of course, is only a pairing. So this means, of course, so we could think about pi. What could it do? Is this guy. It must connect to something, and of course there are different possibilities. In particular, the question is, I have here other pairs. Does it connect to the first or the second of this guy? But if it would connect, let's say, the last one, then this is not possible. Why? Why is something like this not possible?
Because we get a crossing at some point?
Yeah, or we need a pairing of the guys in between, and here I have an odd number. So this means if I have a non-crossing pairing, then the guys which are here in between must be even number, because I also have to pair them in the non-crossing way. So this means if I have an odd number here, and this is the case if I connect the last guy here with another last guy of such a pair, then this is not possible, because I have here an odd number. Not possible because I look on non-crossing partitions. Okay, so such pies are not possible. So this means such a guy must be connected with the first guy of another pair. Okay, so it could be connected. Let's say it could go from here to here. No? This would be okay. I have an even number here, but then if I go, so you see, I'm not connecting it to the next one, but I go a little bit further. I go to one of the later pairs, connect it to the first one. But if I do this, then you see that the guys which are here in between, they cannot be connected to the rest. Because, I mean, those guys are not connected to the rest here, but if I do a connection like this, then they cannot be connected to the rest because, again, I would have a crossing. So this means if I go from this pair, from the last element here, to the first element of the pair which comes later, which is not the next pair, then what is here in between is not connected to the rest. I have no chance of connecting it with the other blocks which I have to the rest. So this means, so this is again not possible, because then this condition that which I have there, that pi sub 0 m hat should be 1 to m, is not satisfied, because then there are things which are not connected. Okay, so this means there's only one possibility which works, namely if I connect the second guy from this here to the first guy of the next pair. So this means I can do like this, then here I connect this to this, and so on, this to this, and so on. And then, of course, the first one here goes to the last one. This is okay. And actually, this is the only possibility which we have for having a non-crossing partition, which also satisfies this quantity. So this is the only possibility for pi. So you see, we just have one possibility, which means we are getting here exactly one. We get what we need. So thus, there's exactly one possibility of pi, exactly one pi, and one crossing pairing of two elements, which satisfies this condition, which satisfies the extra condition which we need in the sum, namely that the maximum of pi and 0 m hat is 1 to m. And this condition is this partition, this pairing is exactly this one. So if I write it formally, so namely this pi is the pairing which connects the first element with the last element, and then it just connects the neighborhood elements. So then it connects 2 with 3, 3 with 4, and so on, up to 2m minus 2 and 2m minus 1. Okay, but then from this it follows that the cumulant, the absolute cumulant of x's, and the x's are the s squared, which, as we have seen, are given by the number of non-crossing pairings of two elements which satisfy this extra condition that I need or join maximum is equal to 1 to m, that this is just 1, because we only have this one possibility. And this is true for all m. And this shows that the x squared, or the s squared, as a semicircle, is actually free cross form. This you get from this formula. Good. Okay, so this shows the usefulness of this formula, and maybe also makes it a little bit clearer what really this condition here means, if you really have to look for such things. Good, but now we still should prove it in general. So we have this theorem, but we still should prove it. So let's do the proof now. Okay, so this is a kind of formal proof where we just have to write down the Möbius inversion and the properties of this embedding head and the properties of the Möbius function. Good, so it's a proof of this theorem. Good, so what we want to calculate this here. So let us start with just writing down. So we have maybe so kappa kappa tau of A1 up to AN. Okay, and of course we know we have to go to the moments, because of the moments we know the relation between the capital and the little a's. So first by Möbius inversion, or the definition of the kappas, we go to the moment functions. So this is by definition the sum over phi sigma of A1 up to AM, and then the Möbius function of sigma, tau, and of course here we are summing over sigma, non-crossing partitions of M elements, and I have here tau, so I'm only summing over the sigmas which are less or equal than tau. That was our definition of the three cumulants by Möbius inversion. Okay, and now, of course, we want to connect this with the little a's. And we have seen, of course, this. We can write the phi of sigma, the capital A's, as the phi of the sigma head of the little a's. That was just the connection, which was also the motivation for defining this head mapping. So this is the same as the sum. Also this here, expressed in terms of the little a's, is phi of sigma head of A1 up to AN. And now actually, you see, I want to go over essentially to the heads, and we have seen that this head mapping also preserves the Möbius function. So if I like, I can also write this Möbius function as mu of sigma head tau head. So this is the Möbius function in NCM, but I want to go over to NC of N. So here I have achieved this, so that I also achieve it here, but we have seen that the head mapping preserves the Möbius function, so I can also write this. This is the same as this. Just expressed in terms of the corresponding partitions in NC of N. Good, but here I still have the sigma, I'm still summing over NC of M, and maybe here I write more precisely when I'm summing here the tau, or the sigma actually is less or equal than tau, and greater or equal than the 0 M. Of course, everything is in NC of N is greater or equal to this. But now you see, I'm summing over sigma, but here I have indexed my guys by sigma head. So actually I'm summing over special sigma heads, which are just images of those sigma here under the head mapping. Okay, but the sigmas which are between 0n and tau, if I map them with the head mapping, and this is bijection from this interval here to the corresponding interval where I put the heads. So I can now rewrite the sum instead of summing over NC of M, summing over NC of N. And then I have replaced everything by things which are living in NC of N. So now let me call maybe the sigma head. Sigma here. Maybe let me just write it again, but now already maybe getting rid of the head. essentially and summing now over the sigma hat, but I'm calling it omega. Sigma hat, I'm calling omega, and then I'm essentially summing here over omega in NC of n, where omega is between 0 m hat and tau hat. Instead of summing over sigma, I'm summing over sigma hat. And the sigma hats, if sigma is between this and this, the sigma hats are exactly those which are between this and this NCN. Because this hat mapping is a bijection of, or an embedding of the process. So this interval here is exactly mapped to this interval here. And then, of course, the quantities which I have here, the sigma hat is omega of A1 up to AN. And here I have mu of omega tau hat. And now I'm just inside NC of n. I'm doing here some over NC of n. But still here I have now the moment functionals, and of course I want to cumulants. So now I do again a Möbius inversion, or the relation between moments and cumulants, but now in NC of n. I write this now in terms of cumulants of the little bits. What do we have? I still have the same sum here. I have omega and NC of n, where omega is between 0 and hat and tau hat. And phi omega I'm writing in terms of cumulants, so I have another sum here. I'm summing, let's say, over pi NC of n, which are less or equal than omega. And then the phi omega are the sum over the cumulants, kappa pi of A1 up to An, and I still have the Möbius function of omega tau hat. Good, now you have this double sum. You do the only thing you essentially can do, just exchange the order of the sums. Now, of course, we want, so you see, we have now here cumulants of the little a's, that's what we want in the end, but of course we have here a double sum and we have the Möbius function, and nothing like this appears in the final result. So we should get rid of some things, and okay, what can we do? We just change the two sums. Instead of first summing over omega and then over pi, we do the other way around. And of course have to see what this means with our conditions. So we are summing, let me write it here. So I'm summing first over the pi's in NC of n, and then summing over the omegas in NC of n. Okay, but what are the constraints? So I mean the pi is less or equal to omega, the omega is less or equal to tau hat. So the pi's which we can have in this sum must in any case be less than tau hat. So here I have the condition that pi must be less or equal than tau hat. And for the omega, so what are the conditions for the omega? I mean, omega must be bigger than this one, and omega must also be greater or equal than pi. So this means the omega, and of course the omega is also less than tau hat. So on one side it's less or equal than tau hat, and on the other side actually we have two conditions, namely it must be bigger than 0 m hat, but it must also be bigger than pi, and this means it must be bigger than the smallest element, which is greater than each of them, which is of course the maximum. So this means omega must be greater or equal than 0 m hat maximum pi. Now you see how we get somehow something like this into the game. Okay, and of course here we still have the same. We have kappa pi of A1 up to AN and mu of omega tau hat. Good, but now we see that actually this kappa pi doesn't depend on the second sum, so we can move the kappa pi here, and then we have a sum over the Möbius function. And there we know something. Let me do this. So I'm moving now just kappa pi over here, because kappa pi does not depend on the omega. So again, so we have again those two sums. The sum over pi, 1 crossing of n, when pi is less or equal tau hat, and then I get kappa pi. So pi is fixed. And I take kappa pi of the little a's, and then for the fixed pi, I'm summing over the omegas, omega in n c of n, such that the maximum of 0 and hat and pi is less or equal omega, less or equal tau hat. So I'm summing over omega, which are between this and this, and I'm summing now just the Möbius function of omega, comma tau hat. Good. But summing the Möbius function over one of its arguments, that argument is running between something here and the second argument. This is something which we know. Actually, this is just the defining property of the Möbius function, that this sum is either 0 or 1, and it is 1 only in this case, and this guy here is the same as this. Otherwise, it is 0. This is just the fact that the convolution of the Möbius function is theta is a delta function. So this sum here is actually reduces just to two cases. It's either 1 or 0. And I mean, this is just the fact that the theta function involved with the Möbius function is the delta function. Because that is what we're actually doing in this sum. And the delta, we're taking it here and here. Delta of this and this is 0 if they are not the same, and this is 1 if they are the same. So this is 1 if this guy is the same as this. So if 0 m hat, maximum is pi, is equal to tau hat, and it is 0 otherwise. Otherwise means it's strictly small. And this maximum is strictly smaller than tau hat. So this means this sum here over the omegas, this gives 0 or 1, and it gives 1 if this condition is satisfied. So you see this gives us a condition of the pi's. So the pi's must satisfy this condition. Then I get here the contribution 1. If the pi's don't satisfy this condition, I get 0. And so I get more or less what I want. Maybe I have now, I'm summing over. I'm summing over pi's in NC of n. Of course, I have this condition pi is less or equal tau hat. But now this sum here gives me the condition that pi must also satisfy this. Otherwise, I get 0 from this summation. So this means I'm actually summing over pi's, which must also satisfy that 0 m hat, maximum is pi, is equal to tau hat. So this condition here. If this is satisfied, then this gives me 1, and I'm just remaining with gamma pi a1 to a1. And you see, we have now more or less what we want. Only here, instead of one condition, it seems we have 2, but actually this condition, that tau hat is greater or equal than pi, is containing this condition, because this here means tau hat is greater or equal to pi, and it's greater or equal than this value. So this condition is not an extra condition, but it's contained here, so we can forget it, and we just have this condition. So this here is the same as just taking the second condition. 0 m hat is pi is tau hat. That's the condition which we have here. So we are summing over the pi's to satisfy this condition. Yeah, that's the end of the proof. So you see it's quite formal manipulations, but we are essentially doing Möbius inversion both on the n and the m level, and then we just use the properties of the Möbius function and also the properties of this embedding tau hat. So we have set everything up in such a way that it goes very smoothly and nicely. Good, and we already have seen that this seems to be at least a useful formula which can be used in some cases. That really we can calculate, let's say, cumulants of the capital A's if we know cumulants of those guys. But now we want to go in the direction that the cumulants have a much more fundamental meaning, that they really can characterize freeness. Oh? Okay, in the and the main this characterization will be of the fact which already we have seen it in a sense when we motivated by the limit theorems, the cumulants. There we saw that if I write, if I have elements where I'm writing the moments in terms of something, which are now the cumulants, and I have another guy where I'm writing it also in terms of the cumulants, and those guys are free, then the mixed moments of those two guys can also be written as the sum of the cumulants, and actually there were no mixed cumulants. There was nothing, no cumulants which were mixing the two elements. And it turns out this is actually the characterization on a very abstract level of freeness, that freeness is equivalent, that mixed cumulants and free variables vanish. That's the main, that's really, I mean, why we do all this cumulant machinery. Yeah? And for proving this theorem here will be essential. Okay, and so we go now in this direction, but maybe the first step for the proof, which will be part of the proof of the general theorem, is to look on a special situation if one of my variables is 1. We know that 1 is free from everything, which means if it is true that mixed cumulants and free variables vanish, then it should be the case that if I have a cumulant where I have 1 as an entry, and it doesn't matter what the other entries are, then this should vanish. Because this would be a mixed cumulant where I have a variable which is free from whatever I have there. Also, this means if I have a cumulant where at least one entry is 1, this should be 0. And so this is on one side a very special case of this general theorem, but it's also something which we have to use in the proof of this general theorem. So let us first look on this. So, anyway. And of course, vanishing of mixed cumulants means that I should have at least 2 variables. So I'm not saying that if I take kappa 1, the cumulant of one element, and I put in 1, that this should vanish because this has always to be 1. But if I have a cumulant with at least 2 arguments, and one of those arguments is 1, then it has to be 0. Good. So that's position 322. So again, in our frame we have a non-group probability space, A5. Probability space. We have cumulants, corresponding cumulants, of course. Kappa n and n. We could also take the extension to the numbers of partitions. So those are corresponding free cumulants. No? Corresponding, of course, means with respect to phi. Cumulant are always defined if I'm given a phi. If I have a non-continuous probability space, I have a specific phi. Good, and now I consider a number of arguments, which are known by n. This should be at least 2, and let's take n arguments and elements and random variables in my algebraic. So consider a1 up to an in A. And now I'm going to make a specific statement. If it happens that at least one of those a's is equal to 1, then the corresponding cumulant is equal to 0. There exists at least index such that AI is equal to 1, so at least one index I between 1 and n. Such that the corresponding variable, namely AI, that is equal to 1, then I'm claiming that kappa n of A1, A2 up to An is equal to 0. So whenever I have such a cumulant. And of course for n equal to 1, this is not true. No? I mean, of course we should know kappa 1 of A, I mean, if I have kappa 1, I only have one argument. Okay, let's say this argument is 1. Then of course this is not 0 because we know kappa 1 is always the same as our phi. So this kappa 1 is just phi of 1. And phi of 1, of course, is always 1. So kappa 1 of 1 is 1, but all the higher kappa n's, if there is 1 between the entries, then it is equal to 0. Good. So the proof is essentially by induction, and it's more or less that the relations which we have are somehow compatible. Of course, 1 is the element where multiplied with something, it doesn't change it. So we can, for example, we can also use this formula here, let's say. I mean, there are many possibilities for proving this, but let us also use this formula. But maybe the proof will be by induction on n. So maybe we first should check the smallest possible case, n equal to 2, to get the induction started. So let's say n is equal to 2. So what I'm saying then, I have k2, a comma 1, let's say. And let's say, I mean, for simplicity, I will consider the situation that the last element is equal to 1. I mean, it doesn't matter. The argument is the same, but I mean, in order to write down concrete formulas and indices, let us assume that an is equal to 1. So I want to show that a1 up to an minus 1 comma 1 is equal to 0. So without assuming the following, that this I is equal to n. The I where I say n. Okay, so here I also take the second element, and then, so what is kappa 2? Of course, we have a formula for kappa 2. This is the variance. So it's phi of the product of the two guys, a times 1, minus the product of the phi's, minus phi of a times phi of 1. And of course, a times 1 is 1, and phi of 1 is 1, so we just have phi of a minus phi of a, which of course is 0. So you see, this is trivially satisfied. And now we do the induction step. So assume the statement is true for all, let's say k less than n, and we want to show it for n. So statement is true for all, let's say k less than n, and we want to prove it for n. Good. Okay, so what do we do? I mean, I want a cumulant where the last entry is equal to 1, and I can also connect this with a cumulant of length n minus 1, where I'm just multiplying the last entry by 1. So I can consider, let's say, kappa n minus 1 of a1 up to an minus 1, and then I'm multiplying it by 1. Because, of course, this doesn't change anything. Good. And on the other hand, by the formula from our theorem, I can connect this with cumulants where I consider this and this as separate arguments. I can say I have here actually n arguments, namely 1 up to an minus 1 and then 1. And here I have multiplied two of those arguments together. So we know that by our general formula, this is given by summing over kappa pi's of a1 up to an minus 1, and then the 1 is the last argument. And the pi's are non-crossing partitions of n elements such that I have this condition pi maximum with 0, n minus 1. So m is m. n is now n minus 1. So I have here n minus 1. Guys, this hat, this is equal to 1n. Okay, well, what is this 0 n minus 1 hat? This tells me where I have multiplied guys, and here I have only multiplied two of them, only the last two elements. So this 0 n minus 1 hat, so this is just the partition where most blocks are singletons. I haven't multiplied anything, only the last block contains two elements, this and this. So I have here 1, 2, and so on, up to n minus 2.
all of those are singletons, and only at the last position I have multiplied n minus first and the last yes element. Oh, okay, so this is just this guy. And now again I have to think what are the possibilities for pi which have this property, which connect everything, which means the two last guys are connected and pi must somehow connect all the rest. So what are the possibilities for this? And of course we can also use the induction that if I have smaller blocks, then I should not connect one with anything else, because I already know that such cumulants is 0. Good, so here are the possibilities for pi's with such a property, so positive pi, which has the property that the maximum of pi and this 0 n minus 1 hat is everything, so it's 1n. So what is the situation? I have my elements, so my n points, and the sigma, I mean it's singletons everywhere, only at the last position I'm connecting those two. And the pi now must connect all the other guys. And of course there's one pi which always does this, namely 1n. I mean in this sum, there's always one term, namely 1n. In this sum, so we are this sum. So I mean, the maximum of this should be 1n, and of course if I take for pi 1n, this does this, independent of what the other thing is. So this means I always have the possibility that I'm just connecting to anything, and of course this gives me exactly the term in which I'm interested, because the kappa pi of this, of course, this is just kappa n of a1 up to an minus 1, comma 1. That's the term which I really want to see that this is 0. Okay, but then there are other possibilities. So namely, I can also connect those guys together by connecting some of them to this guy and some of them to the other guy, because these and these are already connected. So this means, and in a non-crossing way, there are only the possibilities that, I mean, this connects up to somewhere here, and this then connects to the remaining ones. Good. Okay, but this block here, I mean, this contains the 1, and here, those blocks here, they are smaller than n. For those, I already know that the cumulant, which has a 1 as length, is 0. So this means this situation here can only happen if there are no other elements here. So this means I only have a block of size 1 here. So this here is only possible actually for this situation. So I have this, and then I connect here all the rest. Because if this here is connected to anything else, then I would have a cumulant which has an n greater than 2, and by induction hypothesis we already know that they are 0. Because I mean they are smaller than n. So it's only possible for this, and this gives me the contribution. I mean this here is this block is kn minus 1, which connects all a1 up to an minus 1, and this here is just a singleton which contains kappa 1 times 1. But this is just 1. So you see, we have exactly 2 pi which satisfy this property. And the property that the corresponding kappa pi is not equal to 0. I mean, there are more pi's which satisfy this property, but most of them have a corresponding kappa pi. Kappa pi is not 0, then I only have this one. So this means kappa n minus 1, a1 over a n minus 1 multiplied here, this is given by summing over those two possibilities of the corresponding kappa pi's. The first possibility gives me the kappa n of n1 up to a n minus 1, comma 1. And the second possibility gives me the kappa n minus 1 of the first n minus 1 arguments times 1. So plus minus 1 of n1 up to a n minus 1. Good, but of course this term here is the same as this term, because a n minus 1 times 1 of course is just a n minus 1. So this term is here again, so this cancels away, which means that this term has to be equal to 0. This means a1 up to a minus 1 and 1 is equal to 0. Okay, so by induction we have proved this already. Good, okay, so this is the simple situation of the vanishing of mixed cumulants in the case where I look on it where one of my variables is 1, because then I mean whenever I have a 1 in a cumulant, I have a mixed cumulant if there is anything else. But next time then we really want to prove this in full generality. So we want to see that actually we have a really equivalent characterization. Freeness is defined in terms of moments, but this condition is, I mean, if we have alternating center guys, then 5 this is equal to 0. This is something which is not so easy to use. In principle, we know it determines everything, but calculating the formulas for mixed moments is not so easy. Okay, and we replace this, or we show that this definition is equivalent to a characterization in terms of cumulants, the vanishing of the mixed cumulants, which is actually much easier to use. Okay, but so I stop here for today.